The assembly of the outer column and suction bell involves aligning and securing these critical components, ensuring structural integrity, proper sealing, and precise fit to facilitate efficient water intake and smooth pump operation. The outer column and suction bell are carefully lowered, aligned, and secured to ensure stability, proper water flow, and structural integrity. The assembly of the pumping element and diffuser bearing involves carefully positioning the impellers, shaft, and diffuser components to ensure smooth water flow and minimal energy loss. The diffuser bearing, a critical support element, is precisely installed to maintain shaft alignment and reduce vibration. Proper lubrication and alignment checks are performed to enhance durability and efficiency. Precision machining and secure fastening of all components ensure optimal hydraulic performance, minimizing wear while maximizing reliability in high-flow, high-pressure conditions typical of supercritical power plants. Shaft coupling ensures precise alignment, torque transmission, and vibration reduction. The installation of the inner column involves carefully lowering and aligning it within the outer column to ensure proper positioning. Bolted connections are securely tightened to maintain structural integrity. Precision alignment is crucial to ensure smooth shaft rotation and minimal vibration. The inner column supports critical pump components, facilitating efficient water flow and seamless operation under high-pressure conditions. The installation of the discharge head involves positioning it atop the pump column, ensuring precise alignment with the inner and outer columns. It serves as the transition point where pressurized water exits the pump. Secure bolting and sealing prevent leaks and pressure loss. The discharge head also houses bearings and shaft connections, ensuring smooth rotation. Proper installation guarantees efficient flow, structural stability, and optimal performance in high-capacity pumping operations. Connecting to the test loop involves securely linking the pump's discharge to the test system, ensuring proper sealing, pressure integrity, and accurate flow measurement to validate performance under real operating conditions. The bearing housing is carefully installed to support the pump shaft, ensuring proper alignment, minimizing friction, and reducing vibration. Secure fastening and lubrication enhance durability, enabling smooth and efficient pump operation. The installation of the motor support involves carefully positioning and securing the support structure above the discharge head to ensure stability and proper alignment with the pump shaft. Precision is crucial to maintain shaft centerline alignment, minimizing vibration and wear. The motor support must withstand operational loads and dynamic forces, ensuring reliable power transmission. Proper bolting and reinforcement guarantee durability, enabling efficient pump operation in demanding industrial environments. The investment casting process begins with the melting of iron, which forms the base material for the fire hydrant components. In a large kiln, the iron is heated to extremely high temperatures, typically between 2,600 degrees Fahrenheit and 2,800 degrees Fahrenheit. This molten metal is carefully monitored to ensure that it reaches the desired consistency before being transferred into molds. With the molds prepared, the molten iron is poured into the foam molds. This is where the process earns the name lost foam. The foam material evaporates upon contact with the molten metal, leaving behind a hollow metal casting. The precision of the foam mold ensures that every detail of the fire hydrant component is replicated in the metal. This step requires careful control to ensure that the molten iron flows evenly through the mold, filling every cavity without causing defects. After the molten iron has cooled and solidified, the next step is to remove any excess sand and residue from the casting. The upper barrels of the fire hydrant are typically dropped into a large bin to release any sand from the casting process. Once the sand is removed, the pieces are transported via a conveyor to a cleaning room. The caps and bonnets of the fire hydrants are produced in separate areas of the foundry. These parts are made in high volumes, which requires efficient processes to ensure consistency. The caps are sent to robotic machines that perform precise threading operations, enabling them to fit securely onto the fire hydrant. Similarly, the upper barrels are threaded to accept nozzles that are necessary for the hydrant's operation. At this stage, the fire hydrant components are rapidly moving toward the final assembly, and their quality is critically important to ensure that they fit together perfectly and function as intended in real-world conditions. The assembly of the fire hydrant begins with the parts being loaded onto a trolley, which carries them along a pre-programmed course in the assembly bay. This trolley system is guided by electronic indicators embedded in the concrete floor, ensuring that each fire hydrant is assembled in the correct order and configuration. At the assembly station, workers attach the lower and upper barrels, install the operating stem, and connect the bonnet. The oil reservoir is pressure tested, ensuring that it can handle the demands placed on it during use. The entire assembly is then filled with water to check for any leaks before being washed, dried, and painted. After the fire hydrant is assembled and painted, it undergoes a final set of tests to ensure it functions properly. These tests include pressure testing and confirming that the hydrant can withstand the water flow and pressure requirements of a real-world fire emergency. Once tested and approved, the completed fire hydrants are ready for shipment to customers around the world. They are loaded onto pallets and transported to various locations where they will be installed and put into service. Once the fire hydrant components are cleaned and machined, they are primed with an epoxy primer. The epoxy primer is used to protect the metal surfaces from corrosion, which is particularly important for fire hydrants, as they are often exposed to harsh environmental conditions. The primed parts are then moved along an automated line to be painted. This painting process ensures that each fire hydrant component is coated with a durable finish that provides additional protection against the elements, helping to extend the lifespan of the hydrant. The paint drying process is accelerated using infrared heat, allowing the primer to dry quickly while maintaining the quality of the finish. This rapid drying process helps increase production efficiency, which is important when manufacturing large quantities of fire hydrants. In Scranton, Pennsylvania, a significant water main repair was carried out involving an 18 inches HYMAX Large Coupling, a critical component in restoring service to residents without causing disruption. The repair process was well planned, as the water main involved was large and the pipe system had been in place for decades, likely contributing to a leak that needed urgent attention. The first crucial step was to stop the water flow from the affected area, a task accomplished using devices called line stoppers. Due to the large diameter of the main, 3 separate line stoppers were required to effectively isolate the section of pipe being repaired. These devices are especially useful in situations like this, where old water and gas pipes need replacement, which is a common issue in many older eastern cities with aging infrastructure. Once the area was secured and the water flow halted, the focus shifted to exposing the leaking pipe. This involved cutting through the thick, cast iron material with a specially rigged chainsaw that sprayed water to keep the pipe cool during the cutting process. The process was slow due to the thickness of the pipe, which exceeded an inch in thickness and weighed over a ton for a single section. The next challenge was replacing the damaged section with a new one. The HYMAX Large Coupling played a vital role here, as it enabled the new section of pipe to be securely attached to the old pipe. The coupling, known for its robust design, was used with collars to ensure a tight and secure connection. The entire team worked carefully, using power drills followed by hand tightening to secure the coupling, making sure the pressure balance between both sides of the line was maintained to avoid further leaks. Throughout the entire repair process, one of the most impressive aspects was that no customer lost water service. Thanks to the careful installation of the line stoppers before any work began, the Pennsylvania American Water Company ensured that residents had continuous access to water, even during the extensive repair work. Once the final connections were made and the water pressure was properly balanced, the water flow was restored. The hole was filled, paving was scheduled, and traffic was back to normal by the next morning, marking the successful completion of this large-scale water main repair. The electroplating process used in the manufacturing of taps, mixers, and fittings involves several precise and controlled steps to ensure high-quality, durable, and visually appealing components. The process begins in the foundry, where raw metal components are cast into molds. Once the components are cast, they undergo machining to smooth out rough edges, followed by polishing to give them a shiny, smooth surface. After polishing, the components are ready for the electroplating department. This step involves the electrochemical plating of nickel and chrome onto the metal surface to protect it from corrosion and give it an attractive finish. The components are first loaded onto jigs or hangers and coated with rubber before being transferred to the electroplating section. The electroplating process involves multiple cleaning and preparation steps. Components are dipped into tanks for cleaning, starting with ultrasonic cleaning to remove any polish residue from hard-to-reach areas. Next, they undergo electronic cleaning to eliminate any oxides or scale, ensuring that the plating adheres properly. Even microscopic particles are removed during these cleaning stages to prevent defects in the electroplated layer. Once cleaned, the components are dipped into a nickel solution bath, where a thin layer of nickel is deposited as a foundation. The process is repeated several times to build up the layers of nickel. Afterward, the components are rinsed and immersed in an acid bath to prepare them for the chrome plating. In the final step, they are dipped into a chrome bath, which gives the components their shiny silver appearance. The entire electroplating process lasts about 90 minutes and is carefully monitored to ensure quality. After plating, the components are inspected for defects like scratches or bubbles before being packed and sent for assembly, ready for use in everyday products like taps, mixers, and fittings. The DVSH-RO pump achieves efficiencies exceeding 90% through advanced hydraulic design and precision manufacturing. Its double suction impellers and optimized hydraulics reduce energy loss, while engineered thermoplastic wear rings minimize friction. The double volute casing ensures balanced forces, reducing strain on components and enhancing long-term performance. This results in minimal energy consumption and optimal efficiency in reverse osmosis processes. The DVSH-RO pump handles flows up to 7,000 cubic meters per hour, supporting large-scale desalination plants with high-capacity, efficient performance. The DVSH-RO pump offers market-leading efficiency by reducing energy loss and maintaining low NPSHR net positive suction head required. Double suction impellers balance axial thrust and minimize radial forces, enhancing stability. The heavy-duty shaft and rotor ensure reliable, high-performance operation under critical conditions. The engineered non-metallic wear rings in the DVSH-RO pump are made from high-performance thermoplastic materials that provide smooth operation with minimal clearances. These wear rings reduce friction, improve efficiency, and extend the lifespan of the pump. Their renewable design allows for easy replacement, ensuring continued optimal performance while minimizing maintenance costs and downtime in demanding reverse osmosis applications. The DVSH-RO pump offers multiple bearing configurations to accommodate varying operational needs. These options provide flexibility in optimizing support for the shaft and rotor, ensuring stability and reducing wear. Depending on the application, bearing configurations can be tailored to handle specific loads, enhancing the pump's reliability and performance. This adaptability minimizes downtime and extends the overall lifespan of the pump. The DVSH-RO pump is built to the highest manufacturing standards, ensuring precision and durability. Each pump undergoes rigorous quality control, including advanced testing at Flowserve's 18 megawatts testbed. Materials and components are carefully selected for corrosion resistance and optimal performance. The manufacturing process prioritizes superior craftsmanship, reducing imperfections and enhancing reliability, making the pump ideal for demanding desalination environments. Applying anti-seize lubricant to the saddles. Carefully slide the shaft with bearings into housing for alignment. After positioning the shaft, use a shaft wrench to secure and adjust its alignment, ensuring proper fit before tightening the assembly components. Position the shaft clamp over the bearing assembly, align it correctly, Then tighten the bolts securely to ensure stability and proper shaft operation. Placement of the shaft O-ring. Adding anti-seize lubricant. Placement of the release collar and second O-ring. Adding the sleeve spacer. Prepping the expeller ring for installation involves several crucial steps to ensure a proper fit and optimal performance. First, thoroughly clean the expeller ring and surrounding components to remove any debris, dirt, or old grease. Next, inspect the ring for any signs of wear, cracks, or defects that could affect sealing performance. Apply a thin layer of grease to the shaft sleeve to reduce friction and facilitate smooth installation. Ensure that the expeller ring is correctly oriented before sliding it into position. Finally, check the alignment of the expeller ring with the shaft and other sealing components before securing it in place. After installing the expeller, the next step is placing the impeller gaskets. These gaskets create a tight seal between the impeller and the backliner, preventing slurry leakage and ensuring efficient pump operation. Carefully position the gaskets on the shaft, ensuring proper alignment with the impeller mounting surface. Apply a thin layer of grease or anti-seize to the gasket surfaces if required, which helps with sealing and future disassembly. Double-check that the gaskets are seated correctly before proceeding with the impeller installation. Apply anti-seize to the casing bolts threads to prevent galling, corrosion, and ensure easier future disassembly during maintenance or repairs. Carefully align the pump casing with the backliner, secure it with bolts, and ensure a proper seal to prevent leaks. Rotate and tighten the impeller onto the shaft, ensuring proper clearance with the casing, then secure it to optimize pump efficiency and performance. Evenly tighten the casing bolts in a crisscross pattern to ensure a secure seal, preventing leaks and maintaining pump structural integrity. Carefully extract old windings using specialized tools to prevent damage. Install a precision-engineered commutator to ensure optimal electrical contact. Test insulation integrity by applying high voltage to ensure durability. Check for potential short circuits between armature bars for safety. Insert high-quality insulation into armature slots, enhancing dielectric strength and preventing electrical breakdowns before installing the new coils. HiTRAX coils provide superior insulation, enhancing motor longevity and performance. Carefully insert HiTRAX coils into armature slots, ensuring proper alignment and secure placement for optimal electrical conductivity and motor efficiency. Positioning coil ends into new commutator. Slotting wedge to secure coils. Before TIG welding, the armature is prepared by ensuring the coils are properly positioned and securely held in place. The surfaces to be welded are cleaned and free of contaminants to ensure a strong bond. Protective measures are put in place to prevent overheating or damage, and precise alignment is checked to ensure accurate, high-quality welding of the coil ends. The VPI process involves setting precise pressures in impregnation tanks, ensuring resin fully saturates the windings for enhanced insulation. Resin is carefully introduced into the impregnation vessel, ensuring complete coverage of the windings to improve insulation and durability. Once the resin has fully impregnated the windings, the armature is carefully removed from the VPI tank for curing. The armature is banded with high-strength materials to secure the windings, providing additional mechanical support and ensuring the coils remain firmly in place during operation, preventing any shifting or damage. A dial indicator measures the armature's alignment, ensuring it rotates smoothly and evenly, confirming no warping or misalignment during operation. The initial skim of the commutator involves carefully removing any surface irregularities, rough spots, or wear to create a smooth, even surface. This process helps to ensure optimal contact between the commutator and the brushes, improving electrical conductivity and reducing friction. It is performed with precision tools to prepare the commutator for further refinement and enhance motor performance. The final skim uses diamond tip tooling for precise, ultra-smooth finishing, ensuring an optimal, wear-resistant commutator surface for improved performance.